Okay, I am going to quickly go through the last part of Chapter 8 and then do some review. So exceptional flow control is where we're at. So we talked a bit about changing your control flow based on a system event, basically hardware interrupts. So yeah, these were low-level mechanisms, and then we talked a little bit about how we do process context switches in response to getting an interrupt or a fault or these sorts of things. So as we go up the stack, we're going to talk about software exceptions and software signaling. So yeah, this is just a little bit of a recap. We talked about hardware and operating system mechanisms for interrupting control flow and executing handlers. So we're going to talk about the same thing in the software domain. So how kernel software and other applications can give you events that force you into a handler, an exceptional event handler. So to motivate why we need this, we're going to go back to a shell example. So any shell that when you log into Linux Lab or remotely from anywhere, on that system that you SSH into, you have a shell. And this is the command line that you type a command and it spawns off that command and executes it. So this is a canonical example, a simple example of what a shell looks like. You read from the command line, you read some string, that is the instructions that the user types in, and then, or you allocate that, and then while forever, you print the shell prompt, you get the next line of the command, so this fgets command line. If you try and get it and you get an end of file character, which is what this thing says, then you exit the shell. So that's Control D. If you hit Control D in a shell, that's the end of file character, and then you exit. Otherwise, you'll call this evaluate the command line, and what that is something that looks like this. I'll walk through here. And before I walk through here, the reason why this slide is there is that sometimes in your shell, if you put the and after the command that you want to execute, this will stick it in the background. It'll say, don't wait around for this thing to finish. Just put it off into the background and then prompt me for the next command. This is a problem if you want to start up a server and you still want your command line, right? So like if you're starting up a web server, you would say, oh, HTTPD and stick that in the background, and it's sitting there processing network requests, and then you as a user on this shell can continue to type commands. So that's what we want to implement eventually in our shell. Okay. So this is an implementation of that using this eval function. In this function we have the arguments. So we're gonna construct arguments to pass to the command we execute. This buffer is the command line that we're gonna parse, and we're gonna need to parse this to pull out all the binary and the arguments to that binary. We're going to have this flag that says whether or not this job should run in the background or the foreground. So it's basically going to take a look at the end of your string and see if there's an and there. And say, put it in the background if the and is there. And then the PID, just a variable for the PID. So we'll copy the command into a buffer, and then we'll parse it into argv to get the arguments. And then we will, as a return of this parse, we're going to say whether or not we're going to need to put it in the background or whether or not we can actually wait for it to finish in order to give you the next command prompt. If argv is null, then you basically hit carriage return and didn't give it a command. So that should just return, and then you'll get the shell prompt again. If it's a command that the shell can handle directly, the shell will handle it directly. If it's not, then you've parsed out that command line into argv, into this data structure argv, which is the argv that you now are going to use to do a fork and then an exec. And part of the exec is the actual command that I want executed, which is the first string in that argument, followed by the argv data structure, which we'll just assume this parse line gives us, and then whatever environment variables. And then if this thing fails, that means the execve will actually return. And because an execve that returns is actually an error condition rather than completely going off to whatever it needs to do, that's what this this set of statements does. If the parent, if you decide not to put it in the background, so if you are launching that command and waiting for it to finish, then what you will do is you will do a wait PID on that. So you save the ID, the PID of the child, and then you can explicitly wait for that child to end, and then you can reap it and return, and then go to the next command. If it's in the background, then all you do is say, okay, I'm going to print the child PID, print the name of the command, and then return you back to the prompt. And you can see this when you type this in the command line. It'll just print these two things and then give you the shell prompt again. Meanwhile, that command that you spawned off is still there running. Yes?
Do you know, because it's a child of this program, doesn't that mean that if you close your shell, that it also closes that program?
Yes. Well, yeah. It belongs in the same process group. So typically, by default, it does. It closes all of it down.
Is there a way to send the command to make it part of a different process group? Or?
Yeah. So yeah, if you want to start it as a daemon, there are different Unix systems handle that differently. But yeah, there are options of spawning that off and saying you don't kill yourself when the parent goes away. Yeah. Yeah. No hub is one of them. Yeah, because that signal goes to both of them. Beyond the scope of this class, though. Yeah. The daemon says the shell that spawns me off, if it dies, don't kill the child, basically. Because we'll talk about this later. There's this notion of process groups in Unix, and when you kill the main process group for the parent, the rest of the children get destroyed also. You want to avoid that. So that if the parent so you want to be able to control that, I should say. So that's sort of out of the scope. That's more of a operating systems thing that you'll get hopefully next quarter or your next course. Okay. So there's a problem with this shell implementation. So it correctly waits and reaps the foreground jobs. So we remember the zombie children. So we don't want zombies running around on our system. And so the foreground process is fine, right? As soon as it ends, I've done a wait PID on that child, and I'll clean it up. As soon as I do that wait PID, the exiting child gets cleaned up, and it goes away. The issue becomes is that process that I put in the background, if it actually finishes, there's nothing in this shell program that's going to wake up and reap that child. There's no other wait in that program. It's only waiting on the, if you see this, the only wait I do is if it's in the foreground. But then how do I know to sort of reap a child? Do I keep on checking? Do I periodically poll all my children to see if they died? Or is there another way? So the punchline is there's another way.
But yeah, the children tell you that it's going to commit suicide.
No, the child tells you that it died, basically. It's, the child dies, and actually the operating system, the bystander, the operating system bystander says, your child died. It's basically what we're going to talk. And that's a signal. So that is a roundabout way of motivating a signal. You need some software mechanism for the operating system or other processes to say, hey, you know what, something happened over here. You're going to have to run a handler. Yes?
So you're faking the death of the child?
You could fake the death of a child by sending that signal.
Yeah, that's what I mean.
Oh, no, but this is a legit child died signal. So if the child dies, so the background child, if it dies, or if it gets destroyed, it needs a way of notifying the parent that that has happened so that the parent can then reap that exit status. Otherwise, that child is going to sit around forever as a zombie. And we saw that in the previous 2 classes ago.
Is it possible for a program to, if it's a child, to send that signal but not actually die or something?
I believe so.
Isn't that kind of like exploitable?
I don't know for sure. Don't know, actually. I'm going to say don't know on that one. I've never tried it. But yeah. Not sure. I think you can send the signal, but the subsequent wait is going to fail. So the signal is going to get delivered, say, hey, one of your children died. But when you actually do a wait on that, it's going to be like, no, it didn't. It's still there. Basically, that call won't succeed in the operating system. That's my answer. Yeah. Okay. So this alert mechanism is called a signal. And signaling that a child has died is only one signal. There's a whole bunch of other signals that are there. But let's define what a signal is. A signal is a small message that notifies a process that some event has occurred, some type of event, because every signal has a type, and it's the number associated with the kind of signal that you're trying to send. It's just like an interrupt has an interrupt number to determine whether or not it's a keyboard interrupt or a network card interrupt or an I/O interrupt. So this is a kernel abstraction for exceptions. And the signal itself is sent from the kernel. And it's sent from the kernel either because the kernel has witnessed something that it needs to notify the process with, or if another process on the system wants to send a signal to you. It'll go through the kernel. So the signals are identified by small integers from 1 to 30. And these are all defined by the kernel-defined types. So a kernel, the way signals work is that if the kernel wants to send a signal to a process, it just updates some state in the context of that process. And then when the process wakes up from being swapped out of scheduling, when the process wakes up, it's going to go and look at that state, and then if there are any events that have happened, it's going to handle those. Okay. So here are some examples of signals. Control-C from the keyboard is SIGINT, which is ID 2. If you have an unkillable program, like if, say, somebody has decided to handle SIGINT, and you really want to kill that program, there's a SIGKILL, which is uncatchable, which will cause that program to terminate. So if you started a command that you haven't been able to kill,
Like Vim, you can't kill it with Control-C.
oh yeah? Okay, if you really want to kill that Vim, send it a -9, and then you'll kill it.
I have a question. I mean, for the CTFs, you have to be in a different terminal, but like you just press Control-C and then you just type kill and you put 9, and that's how you execute from the same shell, or you always necessarily have to open a new shell?
You do not always have to open a new shell to send a signal to that process. So that last CTF level, it was laid out that way because it's easier on the screen to do it that way rather than to try and do it all within the one screen itself. But yeah, that's what the CTF level is, for you to get experience using these different signals and to see what different signals are available to you on the Unix system. And then these are some of them. There's a segmentation fault, which is basically if you give the operating system a virtual memory address that doesn't exist in your process's address space, what happens is, and you guys have probably seen lots of segmentation faults in this class. Well, not lots. I don't know. Maybe you haven't seen any because you're awesome programmers. But if you give it an address that does not exist, the operating system will send you the segv signal, and then by default, your program is by the default action is to terminate on a segmentation fault. But you can actually catch this and do something else if you wanted to. Yeah, if you wanted to.
Backtrace it.
Yeah, you could say, oh, just ignore that. Keep going. So you could do a core dump. Well, the default action is to dump core, but this can be changed as well.
You could core dump and keep going, right?
You could core dump and keep going if you wanted to. Yeah. But yeah, so you can actually, and I'll show you how you can do this. Write your own handlers for these signals, and then you can write a C program that's uninterruptible and has no memory errors, because I'm going to catch segmentation faults and keep on going. That's like the PHP way of doing things. I'm just going to, whoa, look at all these errors. Let's just keep going.
So computer on fire?
Yeah.
No? Okay, keep going.
Yeah.
So when you do a sudo -9-1, is that a kill?
A sudo kill-9, that will kill, and then do 1. Yeah, that'll shut your machine down. So yeah, so he's talking about the PID number 1 is the init process. And if you do an uncatchable kill on the PID process, typically it will kill all the children, which means it'll kill everything.
Tell everything to shut down.
So you've done that before?
Well,
And is that what it does?
Do it
And that's what it does.
On a machine that I couldn't get to shut down, it'll
And it,
all the processes and then you can power it off.
So we can try to do this.
well, you don't have the permissions for that, but like on your own, yeah, that would be something cool to try. I've never tried that before, but that's a different way of shutting down your system, for sure. All right, and then if you look down here, the last one is sigchild, right? This is the signal to get that you get whenever one of your children has terminated and is ready to be reached. So.
The default action is ignore.
Ignore that child. It doesn't need a coffin or a funeral at all.
You're that parent because you're ignoring your child, even after it's died. You're still ignoring it.
Yeah, that is bad parenting. That's too bad.
I should have worried about it. Let someone else take care of it.
Yeah, that's too bad. So there is a programmatic interface to send signals to other processes, and this is the kill call. And typically, it just takes a signal number and a process ID to send it to. So that's what this prototype is. It's got the PID first, and then the signal number to send it. We talked a little bit about processes or process groups. So there is this notion of every process has a unique process ID, but then processes can belong to a process group. So these are, for example, the shell, all of the different programs that it spawns, will typically belong to the same process group as the shell itself. And then when you kill the shell, you will kill all the other processes in its group. And the way to kill an entire process group is to send this signal, and rather it being a positive PID, you would send it to the negative PID, and then it will treat that as a process group, and then kill everything in that group. And that's just for information. I don't expect, if you ever come across this, that's what it is, but it's not too important for this class. What's it?
It's Googleable.
Yeah, that's Googleable. Okay, so here's an example of that fork program using the kill function and then using the wait. So again, we have this loop here that spawns off a whole bunch of children, and these children will loop infinitely. And the results of this fork will be saved in this PID array. Okay, so this gets you n children, and with each of their PIDs in this PID array. And then for 0 to n, I am going to sequentially kill each one of these children with a sigint. And you can see here, this is what happens. You increasingly go from the lowest, the first child to the last. And then in a loop, you then do a wait on this child. This is not using signals, or this is sending signals. So if you look at this, this is sending the SIGINT, but it's not using sigchild in any form, as we were looking at earlier. And then you will sequentially wait on each child here, and then it will be terminated with an exit status or terminated abnormally. And because you killed it with SIGINT, all of these children will be terminated abnormally because they didn't send you a status code, basically. They were killed. And then if you look at this, you can see the ordering is pretty much arbitrary, right? Because all of these things are being handled concurrently, and the ordering in which processes run and are swapped in and out can be arbitrary. So you can see the ordering. The order at which you kill is different than the order that you get the weight statuses back. Okay, so this is what happens when you receive a signal. So if you're the receiver and you're running along here, conceptually, if you get the signal, what's going to happen in your program is that you're going to all of a sudden save your current state. You're going to switch over to a registered signal handler. So every program has to register handlers for every single signal that it can be delivered. And a default set will be instantiated for you. And so when you get a signal, you will execute the signal handler that corresponds to the kind of signal that you got, and then return back to the next instruction that needs to be executed from where you were interrupted. All right? So it's very similar to getting a hardware interrupt, but this is done in software. Okay, some terminology. A signal is pending if it has been sent to that process but not yet received. So that little piece of state that the kernel is sending the process, it takes a while between when the kernel sends it and when the process actually receives it. And so the way it's done, when in between those two times, the signal is considered pending. One of the important things about pending signals is that they're not queued. If you get another signal of the exact same type while one is pending, it's basically like nothing happens because there was already one queued up. So there's already one set, and there is no queue that will increment a counter based on the number of signals that you were sent of that type. Yeah.
Programmatically, how do they actually check for a signal? Does it happen at the initialization of that program coming back into the processor space?
That's exactly it, and we'll show a picture of this. But there's only one bit per signal that says signal received, and that's important because for correctness, you have to know that there's no counter that counts how many signals you got while you were swapped out. Okay, so a pending signal is received at most once, even though multiple signals could have arrived of that same type. Okay. The other thing to note is that the process can block the receipt of certain signals. So if you don't want to hear about segmentation faults, you can actually say, okay, I'm going to block the segmentation fault signal. Yeah, and I'm going to keep on going. And you can do that for any of the signals.
You said that 9 is not patchable.
Except for 9. Yes. Okay. So, the way this is implemented is that the kernel maintains a bit vector for the signals that are pending and a bit vector for the signals that you want blocked. And based on those two vectors, it determines whether or not you have to process a signal or not. Okay? So, let's see here. So, when a process is ready to be run, so this is the details of how signal handling is done. When the kernel is about to schedule a process to run, then what it does is it computes on that process. So in the process's state, it has a pending vector and a blocked vector. And what it does is it computes this pending but not blocked bit vector. And this is the set of signals that the process must handle. And when the process is scheduled to run next, the kernel forces the process to run all of the signal handlers for all the signals that fall into this category. All right? So if this set of signals is 0, then you allow the process to do whatever it wants to. But if it's not, then you basically go from the least significant bit in this vector, and you force that process to run its signal handler for that process number. And then you repeat until all of the signals have been handled. So, okay, so this is what it looks like. You get a signal that's delivered to process A here. But in order for process A to actually get that signal, it has to be swapped out for a different program And then the kernel has to decide to swap that process back in. And it's at this point where this process gets swapped back in that process A is forced to receive that signal. And this is just the way it's implemented in the operating system. Yeah.
Are there ways to like force signal checks? Like if you have a set of like a statement of your code that you need to not have like switched out or something like that, can you force a signal check before that and then stop?
Not that I know of. Not that I know of. I don't think this is something that's readable to the user process. The bit vector, the block vector is though.
The block vector is the non-block.
I don't think so, but I could be wrong.
I was just
Okay, so each signal type has a predefined default action, so you're not instantiating 30 signal handlers when you're writing your C program. You instantiate 0 of them, and then you rely on all the defaults. So you can either terminate on a signal, you could terminate and dump core if it's a segmentation fault, for example. That's what the default is for that. You can stop until you're restarted by a continue signal, or you can just ignore the signal. So those are your default actions. But you are allowed to install your own signal handler. So this is the C library call for registering your own signal handler on a specific signal number. So if I want to catch the segmentation signal, I would say signal, and then it would be sig_seg_v, which is 11, but I would use the constant because it's a nicer way of labeling it. And then I would give it a function pointer. So I would define the name of my handler as, say, I'll just call it handle. And then I would say, this is a pointer to handle, and then that registers my signal handler to run. Okay. So, and then after I instantiate the signal handler to run on that signal, it's called installing the handler. And then when you are given that signal, this handler will catch that signal and handle it. All right. Okay, so here is a simple example of signal handling. So in your main program, you say, I'm going to catch SIGINT. I'm going to disable Control-C, basically. So, and I guess this is what Vim does. It must catch. In fact, you can actually look at the binary of Vim and see it call signal and install something on Control-C. But this says, for that SIGINT handler, SIGINT signal, I want to go to SIGINT handler, which I have defined up here. I don't want you to do the default. And so this will install the handler, and if something is wrong with the installation, it'll print an error. And then what I'll do is I'll just pause. Now this program is going to wait for a signal to be delivered. So if I hit Control-C, it's going to now, instead of terminate, it's going to go to the handler that you installed. And then in this case, rather than exiting cleanly, it will print a message. And then sleep for 2 seconds, print another message, sleep for 1, and then finally exit. So this is a delayed Control-C interrupt. That's basically what that is. Are there questions about this?
Yeah. Does it have to be done inside of main, or can that actually be instantiated before you actually call main?
There's things you can do before the call for main, but you as a user program would probably just do it in main. Yeah, you would register it all in main. Okay, so here's another example. I install on Control-C another handler, and this handler will print this message and will print count. And you see count is a global variable that's set to 5. And then it will decrement count, and it will check if count is 0, and only if it's 0 will it exit. If the handler finishes, then the semantic is that it's going to return back to the instruction that it was executing when it got that signal. And if you look at what main does, it establishes that handler, and then it does an infinite loop. So when you send Control-C, it's going to run this handler for the first time, and then return back into this infinite loop. And then you do Control-C again, and it'll do this again. And meanwhile, it's decrementing the count. And it's only on that 5th Control-C that it's going to actually exit. So this is the way of sort of programming your signal handler to do something like this. And then you can see a run right here. Does that make sense? Yeah.
That count would actually be above main in the stack, right?
This is a global variable.
Yeah.
This goes into the read-write data section, which is actually down towards the text section. So this is not a local variable. All the local variables are stored on the stack.
Yeah.
This is a global initialized variable.
So it'd be way down.
Way right after the text segment is your read-write data section for
Yeah.
globals. That's where it would be.
But when it's read into memory for like runtime, so in runtime, would it be above the stack for main, or would it be down near heap?
Oh no, it's still down. It's actually below the heap too. It's
Oh,
actually
so
in the
it's-
low parts of memory, the right after the text section.
Okay.
After you load this, yeah. Okay, so let's go back to this this fork example. I am going to, in this case, install a signal handler on Control-C, and then I'm going to start forking off. So in this case, both the child and the parent have this SIGINT handler installed. And then I'm going to do what I did before. I'm going to fork off all the children. I have n children. And then I'm going to do go through this loop again and kill each child. And then I'll I will reap each of the terminated children by doing this loop. And this is what you get. You can actually see each child when it gets this Control-C that the parent sends it. You can see that each child will now run this interrupt handler because that's what you installed. And what this thing will do is it'll say process %d, receive signal %d, and then it will do an exit. So this is where you get the extra prints. So each child, as soon as it gets the Control-C, will run its own interrupt handler, or SIGINT interrupt handler, and then we'll print that and then terminate. Does that code make sense?
So pretty much that what you did in the CTI, kind of, when you're writing it.
Yeah, similar. So there was one where I wanted to get rid of seg faults, and that's I just wrote a handler to catch that seg fault.
There was the last couple when you're doing signal handling and stuff. You have like, the child with this thing, print this, and this one thing, and you have it print another thing and then add something else.
Yeah, so that was actually a student designed one.
Yeah.
It was brilliant, actually, the way she had sort of structured. She had a state machine for her program that kept track of which part of the signaling mechanism she was at. So yeah, I was like, wow, that's pretty cool.
That's super cool.
Yeah, that was a really nice level, which is why it's in there. Okay, so let's go back to the shell example because we want to use signals to fix this thing. So how are we going to reap a background job here that has finished? What do you suggest that we do?
Have an event handler for when you get a kill on a wait process or on
Which signal do you want to install the handler on?
probably child.
Sig child, yep. And what do you want to do when you get a sig child?
Probably pull the child, see what if it's trying to exit or if somebody else is trying to kill
The
it.
sig child means that I already died.
Oh, so child. So what's the thing if somebody wants to like send it to a child and then they can't? Or the child doesn't receive or something.
Something else? Let's go back to what would you want to do if you got a... So here, the background process, if you get a sig child, this means that that child has exited. What do you want to do? So you install a signal handler on sig child, but what should you have it do?
Look at the child's result.
How would you do that? Which call? Wait.
With the child ID.
With the, if you know which child you're waiting on, but you might not. If you spawned a whole bunch of children, you know you got some child to terminate. If you wait on the wrong PID,
Oh, you could be waiting.
you could be waiting forever unless you know to not block. So what the sig child does, it doesn't tell you which child died. It just told you a child died. But yes, what you would want to do is on that SIGCHILD handler, you want to do a wait to clean up. So that's what this parent needs to do. Set a SIGCHILD handler that will go and you reap the child that it has so that the cleanup can be done. Okay. So yeah, so on this SIGCHILD, you want to write that SIGCHILD handler that does the wait. And that's pretty simple. So here's an example of doing exactly that. So now I have here, this is my parent. I'm going to install a SIGCHILD handler, and the SIGCHILD handler will now wait on whatever children have sort of finished, and then it will subtract a count. So count is n, and what I want to do is I want to run this. I'm going to fork n children, and then I'm going to, while count is still greater than 0, I'm going to pause, and then as children finish, I'm going to get SIGCHILDs, and then I'm going to run this SIGCHILD handler and then decrement the count by 1 every time I get a SIGCHILD. Okay. So, is there a problem with this code? Does anyone see an issue with this? Will this always terminate? Or can anyone see a condition where this thing will hang forever?
The if could I assign to fork with 0.
Where are you at? Assuming this all works, the fork.
Okay.
What about the while?
This is pausing, and then as soon as you get that nth child, as soon as this goes to 0, then this will get out of this while loop and exit.
So I guess the only left is that if there. There's nothing like coming there.
What happens if 2 children die simultaneously?
Yeah.
Well, this thing has to wait around to get the signals. Yeah, that's exactly it. So remember, these signals aren't queued. So if 2 children die, one right after the other, they both try and send SIGCHILD to the parent, but because those signals aren't queued, the parent only gets 1 signal. So if that happens, this if statement, which is right, this if statement will only run once.
Which means that no matter what you do, you're still going to have a C count over.
Exactly, which will cause this thing to eventually hang. Yeah.
So what's the solution?
What would be a solution? How would you fix it?
Because like throwing in an extra like wait inside of the while seems like unnecessary. But it seems like, or wait, you can do a time wait, so you can do it like just how.
Wait has a mode where you can do it non-blocking.
To do that. Non-blocking.
Non-blocking wait. Okay, but this is the issue. There's only a single bit indicating whether or not a signal is pending, and even if multiple processes have sent that signal, only that single bit is set, and so the parent can hang waiting for these signals. And so you need to be able to call wait in a loop in order to catch these cases where multiple children are exiting. And I should mention that these binaries here, you can build them and run them, and it's basically this exact code. And then on some of them, you'll see that it'll hang, and then on this one, you'll see if you run it multiple times, you'll hang a lot because of this. Okay, so you want to run this in a loop, so that's what this does. So rather than doing a single if, you're basically checking, and you're saying, don't hang on this wait, just check this status, and then for while this is greater than 0, decrement the counter by 1. So what you're going to do is do a wait PID on each one, and as soon as you're out of children waiting, you can return out of this signal handler. And then this will terminate every single time, basically. So that's what that output is. Okay, are there questions about this before we continue?
Is there a reason why you put it into the handler and not the? So you put the while loop inside the handler, and now let's just say, in case I've gotten multiple signals, I'm going to wait in the signal thing to finish processing all the signals that I could have gotten. Right. That's the reason why we put it there and not the while loop, because for some reason that's where I was.
Yeah, and it makes sense to put that code up here. Like, you could actually wait for it down here, but like, this is sort of where your application's at. Like, your shell logic is here. Why would you, why muddy the waters there by handling your cleanup operations? Especially when this is only going to run when it needs to, when you have a cleanup operation that you need done.
So this eliminates any kind of race condition where you have two.
Yeah, because if there is a race where you do have to, this thing is always going to check, keep on doing the wait until there are no more children left to process. So, yeah.
So it's not going to clear that bit until
The bit does not get cleared until the handler finishes. Yeah. Okay, another signal that you can send is the alarm signal. So when you call this alarm with a certain number of seconds, what this will do is it'll schedule a sig alarm for a specified time interval in the future. And then if it returns prematurely, then the remaining seconds is basically set as a return value. So it's basically similar to a sleep, except it doesn't synchronously block. So the sleep will sit there and block, whereas an alarm says keep on executing, and then later on I'll get a sig alarm that will force my sig alarm handler to run. And then you could do something interesting in the sig alarm handler. Okay, so here's an example of using the sig alarm. So in your main program, I'll establish the handler, and then I'll say, give me an alarm 1 second from now. And in the sig alarm handler, I will print beep. And then if I haven't beeped more than 5 times, I'll set another alarm. And then if it has beeped more than 5 times, I'll print boom and exit. So it's basically going to give you beep, wait a second, give you another beep, etc. And then finally, when it's 5, it hits boom.
I have a kind of rhetoric question now. It's more like philosophical, but
Okay.
so when we have like electronic device, let's say it's a watch or something, do they run some similar type of code inside those devices? Like they don't have x86, they don't have ARM, but let's say like a simple counter, like I don't know.
Same idea. Interrupts, timers.
Yeah,
to do this,
have,
yeah.
like, some similar C code. I mean, that's like electrical
Similar.
engineer mostly.
Yeah, similar kinds of
Okay.
mechanisms exist on every CPU. Yeah.
Okay.
Yeah, so you don't have your calendar app sitting there polling everything. Maybe you do. Well, I guess I've never written a calendar app. I shouldn't speak for that. But yeah, this is
Which is why
more
it's
efficient
just a
than
calendar.
polling. Yeah, more efficient than
Like those watches from the 80s, for example, that they're like the digital ones, I don't know, with a calculator, they have something similar. Like to tell
not
the time.
sure. Yeah, but most microcontrollers have an
Yeah.
interrupt mechanism and a timer mechanism. Those are really fundamentally important things to most CPUs that we know, unless you're talking about asynchronous computers, which don't have that need. But yes, you're correct.
Like for simple devices.
Yeah.
With asynchronous though, don't you still have to have some sort of like interaction between the signals? So you still have signaling, but it's just different kinds of signaling.
Different ways, yeah. Yeah, I shouldn't speak to that, but yeah, that's
Sorry.
correct. All right, so that is the end of chapter 8. I think what I'm going to do now is you guys need a lot of practice on signals, I think. So what I'll do first, are there any questions about signals? Because I think we're going to work through some examples, do some practice for the final now. Any questions? All right. Put this in the book.